Hello students and welcome back. In this chapter we're going to begin our discussion of gases. I'd like to thank Pearson for allowing me to use their Tro educational resources and Beyond Labs for allowing me to use their online simulator. So for this chapter we'll begin our discussion with some equations we'll need for the chapter. We're going to discuss some conversion factors. We're going to discuss the simple gas laws, and we'll finish this video with discussing the ideal gas law. We have some other properties and calculations of gases we're going to discuss in future videos involving this chapter, but for this video I'd like to limit our discussion to the simple and ideal gas laws. We begin our discussion with a little bit of history. On October 24, 2014, a Google executive named Alan Eustace performed a skydive from near outer space. He exited a spacecraft from 25 miles above the Earth's surface, and then he began a free-fall descent and ended with parachuting himself back to Earth. He actually broke a record that had been set 2 years prior by Felix Baumgartner. But why do we care about this event? It's because he needed a spacesuit in order to perform this skydive. Most skydivers don't wear spacesuits, but 25 miles above the Earth's atmosphere requires a pressurized suit in order to keep a human body at the same pressure that they would experience on Earth. And this is the kind of discussion we're going to continue in this chapter. We're interested because we're going to learn how pressure affects volume, how the number of gas particles affects volume and pressure, and we're going to interrelate some different properties of gases with each other and see how these different properties are affected when one of the other properties changes. We begin with learning some different equations that we're going to need in this chapter, and this is just kind of an overview of those equations. First, we're going to learn that pressure is equal to force per unit area. And we're not actually going to do any calculations with this in this chapter, but we will discuss this theoretically. We're going to learn from Boyle's law that pressure is related to volume. And pressure is related to volume by this equation, P1V1 equals P2V2. In other words, volume is inversely proportional to pressure. Next, we're going to discuss Charles's law, which relates volume to temperature. We see that volume is directly proportional to temperature, and therefore we can say that V1 over T1 equals V2 over T2. So we're talking about the volume and temperature under the first set of conditions and how it relates to volume and temperature under the second set of conditions. The next simple gas law we're going to discuss is Avogadro's law, and here we see that volume is proportional to the number of moles of gas. So we can derive this equation, V1 over N1 equals V2 over N2, where N is the number of moles and V is the volume. If we combine all of those simple gas laws, Boyle's law, Charles's law, and Avogadro's law, and we derive a proportionality constant, we'll be able to arrive at the ideal gas law, where we see that PV equals nRT. And so we're going to use all of these equations to do some calculations and learn about the different properties of gases. Pressure is defined as force exerted per unit area, and therefore gas pressure can be defined in the same way. Gas pressure is the force exerted by gas molecules per unit area of a surface. And so these gas molecules are constantly in motion, and their collisions with the surfaces around them cause pressure from the gas. So this is actually what keeps a balloon inflated, or a tire inflated, or a volleyball inflated. So it's the actual collisions with the inside of those surfaces that allows them to remain inflated. But we also have gases in the Earth's atmosphere. So these gases are there basically is a sea of gases all around us in the Earth's atmosphere. And these gases contribute to our weather events. You may have watched the weatherman explain weather events in terms of low pressure systems and high pressure systems. Well, it's that sea of gas all around us that creates these low and high pressure systems. And just like we alluded to earlier, as you move higher into the Earth's atmosphere, as you increase in altitude, gas pressure actually decreases. That's one of the reasons why, if you go to somewhere like Denver, it may be more difficult to breathe or to acclimate to that area, because there's actually a lower concentration of oxygen there, or a lower amount of oxygen there, because the gas pressure is a little lower there, and therefore it may take some time to acclimate to that type of environment. So gas pressure is the result of the constant movement of gases and their collisions with the surfaces all around them. The pressure of a gas can depend on the different properties of the gas, and those properties are the number of gas particles in a given volume, the volume of the container that holds those gas particles, and the average speed of the gas particles. And we're going to learn that that average speed is related to temperature. The total pressure exerted by a gas, in fact, depends on several factors, including the concentration of the gas molecules in the sample. The higher the concentration of gas in a sample, or the higher the amount of gas per given volume, the greater the pressure. And this is one of the properties that we're going to explore in this chapter. Also, as the volume increases, if you keep everything else the same, the concentration of gas molecules per unit volume would decrease. This would result in fewer molecular collisions, which would in turn lower the pressure. So you can visualize that here. So we have a jar containing fewer gas molecules on the left, and it has lower pressure, and a jar with the same volume on the right with more gas molecules, which would have higher pressure. You might have experienced something like that with your ear. You may have gone up a hill in a car and then descend down the hill and notice pressure changes in your ear. So you may have had your ears pop by lowering and then increasing the pressure. So that popping is due to the differences in pressure in your ear. Or you may have experienced something like that in an airplane. Something that is advisable in an airplane is to chew gum. This can help to equalize the pressure in your ear. A barometer is a way that we actually measure atmospheric pressure. And one of the earliest barometers was an evacuated glass tube that was submerged. The tip of it was submerged in a pool of mercury. So we're going to actually see an example of that in just a minute. So atmospheric pressure pushes down on the mercury's surface, pushing the mercury up into the evacuated tube. And since mercury has such a high density, atmospheric pressure can support a column of mercury that's 760 millimeters high. And so that's how we define atmospheric pressure, 760 millimeters of mercury. And that is actually equal to 1 atmosphere. So we see here a barometer where we have a tube that didn't have any air in it, or had almost no air in it, and this was achieved by filling that tube with mercury. Then it's inverted into this mercury bath, which is like a evaporating dish here, and by doing so you create this vacuum in the tube. Now atmospheric pressure is pushing down on this mercury, let's say, bath, and it pushes the pushes the mercury up into the glass tube, and it can support a column of mercury. 1 atmosphere of pressure supports a column of mercury that's 760 millimeters tall. Here we have some common pressure units. We see that atmosphere is what? 760 torr, 29.92 inches of mercury, 101,325 pascals, or 14.7 psi. That's pounds per square inch. So we can use these as conversion factors. So we can say, for example, that let's look at how we would use these as conversion factors. We can say that 1 atmosphere equals 760 torr, and we know that 1 torr is equal to 1 millimeter of mercury, so we could say that 1 atmosphere is equal to 760 millimeters of mercury. So we're going to use those equivalences as conversion factors to do some calculations. So in order to measure pressure, we actually need some instrumentation to do that. And today we have digital instrumentation that helps us with this. We have sensors that are calibrated to measure pressure and even pressures of gases. But traditionally, these were measured with instruments that often contained mercury. We try to get away from that nowadays and don't use a lot of mercury anymore because it is toxic. It's also expensive. But one of the traditional instrumentation devices that we had to measure gas pressure in an enclosed container was a manometer. And this was a U-shaped tube that was partially filled with mercury on one side, and it's connected to a gas sample, let's say on the right, and open air on the left. So the mercury was actually in a U-shaped tube. And we're going to see an example of that here. So we have mercury in the U-shaped tube here. We have a gas sample enclosed by that mercury on one side and atmospheric pressure pushing down on the other side. So it's the relative difference in height of the column of mercury that gives us the pressure of the gas. And of course this would have to be measured against a known standard, and we would get that difference from the standard, and that would give us the amount of gas that we had in our enclosed system. Blood pressure is also measured by using a gas pressure, so we increase the amount of gas inside this blood pressure cuff, and that allows the physician to measure the blood pressure by detecting when he can hear the heartbeat begin and end. Of course, blood pressure can be measured, and we have these blood pressure normal and hypertensive or so blood pressure readings here. This is not actually a medical course, so I'm not going to go into what all of these mean, but normal blood pressure is, say, 110/80, something like that. Now we'll begin our discussion of the simple gas laws. Historically, the simple gas laws were developed by different chemists who were relating two properties of gases to each other. So the simple gas laws describe the relationship between pairs of properties of gases. First, we have Boyle's law. Robert Boyle discovered that volume and pressure had an inverse relationship. In other words, if we increase the pressure, for example here we're adding mercury to a J tube, and we're not changing the amount of gas. So we have the same amount of gas in each of these tubes, but we're increasing the pressure in the tube on the right relative to the tube on the left, then the volume is going to become smaller. So we have an inverse relationship between volume and pressure. You can see that here on the graph, that if we're increasing the volume, the pressure decreases. If we decrease the volume, the pressure increases. So we can derive this equation where we see that P1 and V1, that means under a certain set of conditions where our pressure is at condition 1 and our volume is at condition 1, that's equal to P2 V2 through a proportionality constant. So we can say that P1V1 is equal to P2V2 if all other conditions are not changing. So if we keep all of the other conditions constant, then P1V1 is equal to P2V2. So Boyle's law relates pressure and volume. Okay, and this is if we have, again, a constant temperature and constant amount of gas. Okay, so if we graph then pressure versus 1 over volume, so if we graph pressure versus the inverse of volume, we can get a straight line. So here's a interpretation of Boyle's law that we can visualize here. So if we're increasing if we have a larger volume, it's going to have a lower pressure. Notice the gas particles are further apart. And if we decrease the volume, then we're pushing those gas particles closer together and we'll observe a higher pressure. So let's go and look at a simulation that's going to help us visualize pressure and volume. So we can change the pressure here, but we can't change the volume. What we have is a balloon in an enclosed container, okay, and if we increase the pressure in that balloon, let's see what happens to the volume. So we're increasing the pressure, we're decreasing the volume. And if we decrease the pressure, we're increasing the volume. So this simulation is from Beyond Labs. It's an interactive simulation here. We can even decrease the pressure to the point that the balloon essentially explodes. So you see that decreasing the pressure increases the volume. And so this is also an observable condition in diving, and it's what causes divers to experience the bends if they're not taking precautions to prevent that. So at every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure due to the weight of the surrounding waters. So at 20 meters, for example, the diver experiences 3 atmospheres of pressure. So think about it. If you're right at the surface, you've got 1 atmosphere. If you go down 10 meters, okay, for every 10 meters you get an additional atmosphere. So at 10 meters we've got 2 atmospheres. And at 20 meters then we've got 3 atmospheres. Okay? So according to Boyle's law, what would happen to the volume of air in the lungs if a diver holds her breath and quickly rises to the surface where the pressure drops to 1 atmosphere? So in other words, if a diver is at, say, 20 meters or 2 atmospheres and holds her breath without releasing any air, rises to the surface quickly, then just like that balloon, the volume is going to increase, and her lungs may actually have some damage. So the next simple gas law is Charles's law, where we relate volume to temperature. So the volume of a fixed amount of gas at a constant pressure increases linearly with increasing temperature. So in other words, volume is directly proportional to temperature. So we can say that volume is equal to some constant times the temperature. So if everything else is kept constant, we can derive an equation where V1 over T1 is equal to V2 over T2. So if you think about that, if we wanted to look a little bit into the derivation, we could say that volume at the first set of conditions is equal to some K times the temperature under the first set of conditions. And if we keep everything else constant and only change the volume and temperature, then the volume under a second set of conditions is equal to that K times the temperature at the second set of conditions. So if we solve for K, we can see that V1 over T1 equals to K, and in the second equation, V2 over T2 is equal to K as well. So if we set the K's equal to each other, we can say that V1 over T1 is equal to K, right? Which is equal to, then, if that's equal to K, and V2 over T2 is also equal to K, then that's equal to V2 over T2. So what we get is our final equation, V1 over T1 is equal to V2 over T2. Now let's look at what Charles's law looks like on a graph. So we see here that volume is proportional to temperature directly. So if we increase the temperature of a gas, we're also increasing the volume if everything else is held constant. And we can actually even use this equation to extrapolate back to absolute zero. In other words, as we cool a gas down, its volume also decreases linearly. Now we can make these calculations above, let's say, 0C, right? We have to make that in a relatively warm environment, but we can actually do this, and there are some lab experiments, undergraduate lab experiments, that do this and allow a student to extrapolate back to absolute zero. Now we can't do this in real life because gases become liquids at some point before you reach absolute zero, but if you just consider their gaseous state, you can change the volume and temperature and extrapolate back and determine where absolute zero actually is, which is negative 273.15 degrees C. And if you took a balloon and put it into ice water, you could notice that it changes volume, and then if you put it in boiling water, it would get larger. So if you put it in ice water, it'll get smaller. If you put it in boiling water, it'll get larger. And in fact, if you get a Mylar balloon in a cold store on a really warm day and you carry it outside, it might actually pop if the attendant put too much gas in it, because it can actually, the temperature increases to the point that it can cause the balloon to pop. Alright, so let's see if we can view that. Let's see if we can view that in our simulation here. So visualizing Charles's law, we can keep everything else constant except the volume and the temperature. Well, we can't change the volume here manually, but we can change the temperature. Here we're at 373.15 Kelvin. So what is that in degrees C? We can see that's 100 degrees C. Let's go back to Kelvin, and let's increase the temperature just a little bit. See how that affects the volume. Well, we're not seeing a large effect here, so let's increase it in the tens place. Notice the balloon volume is increasing. Alright? So as we increase the temperature, the volume then increases. And you can see the volume increasing here. Now what happens if I increase it by 100 Kelvin? It gets much larger, and eventually it will again explode. Wow, it's increased a lot more. And notice we're not changing the amount of gas. We still have 0.05 moles until it finally explodes. Next, we'll discuss Avogadro's law, and this relates volume to moles if everything else is constant. So just like before, we can see that volume is proportional to the number of moles, just like volume was proportional to temperature. And this is if we're holding the pressure and temperature constant. So just like before, we see that the volume is equal to some constant times the number of moles. And if we say that is at the first set of conditions, so we say that V1 is equal to K times N1, okay? then let's change to a different set of conditions. So V2 is also going to be equal to that same K, because everything else is constant, times N2. Okay, so if we solve for K, then V1 over N1 is equal to K, and V2 over N2 is also equal to K. So therefore we can say V1 over N1 is equal to V2 over N2. And this is Avogadro's law. And we see that the type of gas doesn't matter. We'll talk a little bit more about that in a little bit. So you can see here that as we increase the number of moles this way, we increase the volume as well. And so they are linearly proportional to each other. As we increase the moles, we increase the volume. And we can actually visualize that in our simulation here. So let's hold everything else constant, and we can't change the volume manually. We have to just change the moles. So let's increase the moles. Whoa, see how much larger the balloon got by increasing it by 0.1 moles? Now by 0.2 moles. Now by 0.3 moles. And what if we go up in this place? And finally it explodes. So increasing the number of moles increases the volume. Which action causes the volume of a gas sample to increase? Decreasing the pressure, decreasing the temperature, decreasing the moles, or none of the above? Decreasing the pressure causes the volume to increase. Finally, we'll discuss the ideal gas law. So we can combine all of the relationship we've discussed so far into a single gas law that encompasses all of them. So volume is inversely proportional to pressure is Boyle's law. Volume is directly proportional to temperature is Charles's law. And volume is directly proportional to moles is Avogadro's law. And so by that proportionality constant, or a proportionality constant, we can say that volume is proportional to the number of moles and the temperature, and inversely proportional to pressure. So we can derive an equation that gives us that proportionality constant. And it turns out for ideal gases, or a gas that has basically the same properties as all other gases, and we're going to talk about what that means in just a little bit, we can derive a constant called the gas constant, okay? And we're going to be using this gas constant to do a lot of calculations as we move throughout the semester. We're going to see that a lot of properties are dependent on this gas constant. So it also is dependent on the units, so we're going to keep our units constant in this in all of our equations. So this equation that we derive is PV is equal to nRT, where R is the gas constant. And this is called the ideal gas law. So if we have constant moles and temperature, we have Boyle's law. If we have constant moles and pressure, we have Charles's law. And if we have constant pressure and temperature, we have Avogadro's law. So from all of these laws together, we can put them together and derive the ideal gas law.